Hey everyone, I'm Chengzu, also known as Chloe, and I achieved a 99 ATAR and state ranked 4th in New South Wales in Maths Advanced in 2025. In this video, I'll take you from the ground up through everything you need to know for the HSC and nothing you don't. You don't need to take notes, just relax and watch. At the end, I'll provide ready-made notes and a helpful study resource based on the exact way I studied for my HSC. So without further ado, let's get to it. A function is one of the most important ideas in the whole Maths Advanced course, because almost everything later is built on it. Trig functions, exponential functions, logarithmic functions, calculus, graphs, modeling, even finance, they all use the same language. A relation is any rule connecting two quantities. It can be written as an equation, a table, ordered pairs, or a graph. A function is a special type of relation where each input gives exactly one output. That is why we use the vertical line test. If a vertical line touches the graph more than once, then one x value has more than one y value, so it is not a function. When we write f of x equals 2x plus 3, we are naming the rule. It means put in x, double it, add 3. For instance, f of 3 equals 2 times 3 plus 3, which is equal to 9. X is the independent variable. F of x, or y, is the dependent variable. The domain is a set of allowed input values. For this function, there are no restrictions on what value of x can be. We can take any real number, double it, and add 3, so the domain is all real numbers. The range is the set of possible output values. If we graph this line, we can see that the y values go from positive infinity to negative infinity. So the range is all real y for this example. Domains can usually be restricted in 3 main ways. Number 1. If there are x values in the denominator of a fraction, the denominator cannot equal to 0. Number 2. If there are x values inside a square root or an even root, the expression inside the root must be greater than or equal to 0. Number 3. If there are x values inside another function that already has a domain restriction, that restriction must also be considered. For example, if f of x equals tan of x plus 1, then x plus 1 cannot equal to pi over 2 plus k pi, where k is any integer. The main functions in Mathematics Advanced with domain restrictions are tan x, sec x, cosec x, cot x, and ln x. The zeros of a function are the values where f of x equals 0, or y equals 0. Zeros and x-intercepts are the same thing. On the graph, these are the x-intercepts. The y-intercept is the value of f of 0, or in other words, the value of y when you substitute x equals 0 into the graph. For 2017 students, there is also one-to-one, one-to-many, many-to-many, and many-to-one. These just mean that one or many x values map to one or many y values. For example, in a many-to-one function, many x values can map to one value. In a one-to-many relation, one x value can map to many y values. In a many-to-many relation, many x values can map to many y values. And in a one-to-one function, one x value maps to one y value. To determine which one a relation is, use the horizontal line test, that is, passing a horizontal line down the function to see if it ever crosses twice. This tells you if the first part is one or many. And then passing a vertical line test to see if the second part is one or many. Functions must pass the vertical line test to be a function, so they are only many-to-one or one-to-one. Functions can also be odd, even, or neither. If a function is even, that means it is symmetric in the y-axis. For example, these are even and these are not. A function is odd if it is symmetric about the origin. That is, if you spin it 180 degrees about the origin, then you get the same curve back. For example, these are odd and these are not. If a function is neither, that means it is neither even nor odd. Algebraically, a function is even if f of minus x equals f of x. That is, if you replace every x with minus x and simplify, you will get the original function back. Algebraically, a function is odd if f of negative x equals negative f of x. That is, if you replace every x with minus x and simplify, you will get the negative of the original function back. Algebraically, a function is neither if f of minus x is not equal to f of x or minus f of x. Now let's learn about transformations. We'll use the function f of x equals x squared as an example as we go. The Maths Advanced syllabus has 5 types of transformations. The first one is a translation, which involves shifting the graph. To shift h units right, replace x with x minus h. To shift k units up, replace y with y minus k. After you replace y with y minus k, often k is added to both sides to isolate y again, which is why it often looks like y equals f of x plus k. The second one is a reflection. To reflect in the y-axis, replace x with minus x. Here, y equals x squared is even, so we don't see a difference. Reflect in the x-axis, replace y with minus y. The minus is often moved to the other side to isolate y, so it often looks like y equals negative f of x. The third one is a rotation by 180 degrees about the origin. This is reflecting in both axes at once, so you replace x with minus x and y with minus y. The minus on y is usually moved across to isolate y, so it often looks like y equals negative f of negative x. For y equals x squared, this gives y equals minus x squared, which equals minus x squared. Notice that for an even function, a 180 degree rotation looks exactly the same as an x-axis reflection, but for other functions it won't, so it's worth keeping separate. The fourth one is a vertical dilation, a vertical stretch or squash. To dilate vertically by a factor of a, you multiply the function by a. That is, replace y with y over a, so that y equals a times f of x. If a is bigger than 1, the graph is stretched taller, an enlargement. And if a is between 0 and 1, the graph is squashed flatter, a reduction. For y equals x squared, y equals ax squared sends the point 1, 1 up to 1a, while the vertex at the origin stays put. The fifth one is a horizontal dilation, a horizontal stretch or squash. To dilate horizontally by a factor of 1 over b, you replace x with bx so that y equals f of bx. If b is bigger than 1, the graph is squashed inwards, a reduction, and if b is between 0 and 1, the graph is stretched outwards, an enlargement. It's a little counterintuitive. A big B makes the graph skinnier, not wider. For y equals x squared, y equals bx squared pulls the point 1, 1 in to 1 over b, 1, while the vertex at the origin stays put. And that's the full set: translation, reflection, rotation, vertical dilation, and horizontal dilation. Enlargements and reduction aren't separate transformations. They're just dilations with a factor bigger or smaller than 1. Now that you know every single transformation, let's learn how to do them together. This often looks daunting because you don't know what to do first, so let's have a look at transformation form. The general transformation form is y equals a times f of b in brackets x minus h plus k. The edits inside the brackets of the function affect horizontal changes. For example, h is a horizontal translation and b is a horizontal dilation. The edits outside the brackets of the function affect vertical changes. For example, k is a vertical translation and a is a vertical dilation. Remember, the outside changes the y values, the inside changes the x values. When a function is in transformation form, you apply these transformations in this order. 1. Horizontal dilation factor 1 over b. 2. Horizontal translation to the right h units. 3. Vertical dilation factor a. 4. Vertical translation up k units. If you want to be really picky, yes, it doesn't matter if you do the horizontal or vertical ones first. But just remember dilation before translation. D comes before T in the alphabet. You can shuffle the order however you like as long as each translation goes after its corresponding dilation. Now let's look at our sine function from before. Y minus 5 equals 6 over 5 sine in brackets 8x minus 4. Let's rearrange to transformation form. Here the function f of x in the transformation form is sine. In transformation form, y is always by itself, so let's add 5 to both sides. y equals 6 over 5 sine 8x minus 4 plus 5. Now, inside the f of x in transformation form, the thing is factorized, so x has a coefficient of 1. So let's look inside the brackets of the sign and see. The coefficient of x is 8, so let's factor out the 8 to ensure that the coefficient is 1. It doesn't matter if we get a fraction. Y equals 6 over 5 times sine 8 in brackets x minus a half plus 5. Now our function is in transformation form, where a equals 6 over 5, b equals 8, h equals a half, and k equals 5. So we would do a horizontal dilation by 1 over 8, then a horizontal translation, a half to the right, then a vertical dilation, factor 6 over 5, and then a vertical shift up by 5. Now with all the theory done, let's look at some functions. In Maths Advanced, you see a lot of complex functions and it feels like you could never learn all of them. But here is the main idea. Once you know the basic parent graph, most graphing questions are just transformations. Let's go through every type of function in advanced syllabus and how to transform them. So instead of memorizing hundreds of separate graphs, track important points, intercepts, vertices, asymptotes, centers, endpoints, corners, and how they move with transformations. Now let's build the graph gallery. A linear function is a straight line where the highest power of x is 1. Its key interest paths are the x-intercept and the y-intercept. It has two forms, the general form ax plus by plus c equals 0, and also the gradient intercept form, which is more popular, y equals mx plus c. M is the gradient and c is the y-intercept. Transformations are not needed to graph a line. 2 points are enough. Find 2 points, usually the x and y-intercepts, and join them with a line. Voila! To find the equation of a line, substitute a point x1, y1 and the gradient m into the equation y minus y1 equals mx minus x1, and simplify to y equals mx plus c form. If you don't have the gradient, get it from 2 points x1, y1, x2, y2, with m equals y2 minus y1 over x2 minus x1. Additionally, you can also use gradient equals rise over run. Parallel lines have the same gradient. Perpendicular lines have negative reciprocal gradients. If you need to find the equation of a parallel or perpendicular line going through a point, use the gradient and the point to substitute into y minus y1 equals mx minus x1. Now, quadratic functions. A quadratic function is a parabola. Its key features are the x-intercepts, y-intercept, axes of symmetry, and vertex. We need to recognize 3 forms of quadratics. The first form is the general form, y equals ax squared plus bx plus c. The discriminant delta equals b squared minus 4ac tells us how many x-intercepts it has. The axis of symmetry is the line x equals minus b over 2a, and it is also the x-coordinate of the vertex. C is the y-intercept. If we need to find the x-intercepts in this form, then we set y equals 0 and factorize, or use the quadratic formula or complete the square to solve. The second form is the factorized form, y equals a x minus m x minus n. From this we can find the x-intercepts with the null factor law, that is, they are m and n. If a is positive, the parabola opens upward, and if a is negative, the parabola opens downward. If you want the y-intercept, substitute x equals 0 and compute. And if you want the vertex, find the average of the x-intercepts to get the x value and sub that into to get the y value. The third form is transformation form. Y equals a in brackets b in brackets x minus h squared plus k. This, though rare, can still turn up. This needs you to know that the parent function y equals x squared passes through the origin and the points minus 2, 4 and 2, 4. Then you can use the transformations and dilations to graph the function. Here is an example. Y equals 5 in brackets 3 in brackets x minus 2 squared plus 4. Here, 3x minus 2 is inside the squared function, so they are in charge of the horizontal transformations. The coefficient of x is already 1, so we can read that we need to do a HT of 1 over 3 and a HT right of 2. Now the vertical stuff. Everything outside the square handles the vertical changes. A equals 5 and k equals 4. So we do a VD factor 5 and then a VT up of 4. So putting it all together, A equals 5, B equals 3, h equals 2, k equals 4. And we apply hd 1/3 and then ht right of 2, then vd factor 5, then vt up 4. Remember, dilation before its matching translation. Let's track the key points from the parent y equals x squared. The vertex 0, 0 doesn't move under dilation. Then ht right 2 and vt up 4 send it to the new vertex 2, 4. The point 2, 4 on the parent gets pulled in by the hd to 2 over 3, 4. Shifted right 2 to 8 over 3, 4. Stretched by 5 to 8 over 3, 20, then lifted up 4 to 8 over 3, 24. The point minus 2, 4 moves the same way on the other side. Now, cubic functions. The Maths Advanced syllabus needs us to recognize two different types of cubic functions without calculus. A cubic function has a basic S shape. First, you need to know what the parent function y equals x cubed looks like. It passes through the origin and goes through points -2, -8, and 2, 8. Now to know cubics in transformation form. Y equals a times in brackets b into brackets x minus h cubed plus k. Let's do an example. Y equals 3 times in brackets x minus 2 to the power of 3. Here, x equals 2 is what inside the function, which is x cubed, so that is what is handling all the horizontal changes. The coefficient of x is already 1, so we don't need to factorize. There is no value other than 1 multiplying inside, so it's just an invisible 1. 1 times in brackets x minus 2. That means we do a hd of 1 over 1, which is 1, so we don't need to do anything, and then a ht of 2 units right. Now the vertical stuff. Outside the cube, we have a equals 3 and there's no k, so k equals 0. That means a vd factor 3 and no vertical translation at all. So altogether, a equals 3, b equals 1, h equals 2, k equals 0. And we apply ht 1, no change, ht right 2, vd factor 3, no vt. Tracking the key points from the parent y equals x cubed, the point of inflection 0, 0 doesn't move under dilation. Shifts right to 2, 0 and stays there, no vt. The point 2, 8 shifts right 2 to 4, 8, then stretches by 3 to 4, 24, and the point -2, -8 shifts right to 0, -8, then stretches by 3 to 0, -24. In cubics, if the x-intercepts are hard to find, you do not need to find them. The key points are where the original origin, point of inflection, is, and also the y-intercept. The form is in factored form, y equals a, x minus r, x minus s, x minus t. Here the key points are the x and y intercepts. In this form, the x-intercepts are visible. Here we can use the null factor law to find the x-intercepts, which are r, s, and t. We can find the y-intercept by substituting x equals 0. The value of a determines which way the cubic goes. If a is positive, it means the cubic starts low and ends high. If a is negative, it means the cubic starts high and ends low. Let's do an example. Y equals 2x, x plus 1, x minus 2. Here the x-intercepts are 0, -1, and 2. A is equal to 2 here, so the cubic starts low and ends high. Subbing in x equals 0 gives y equals 0, so it has a y-intercept 0, which means it goes through the origin. Let's draw it. We'll start low and go up to the first x-intercept, turn around, go down to the second, then turn around, then go up to the third and shoot up. Let's do another example. Y equals x times x minus 1 squared. Here we can rewrite to expand it because it looks kind of confusing. Y equals x times x minus 1 times x minus 1. And a is equal to 1, so we start low and end high. And the y-intercept is 0, so we go through the origin again. Here the x-intercepts are 0, 1, and 1. But hang on, 1 appeared twice. When an x-intercept, also known as a root, appears twice, we call it a double root. When we have a double root, instead of the line going through the root, it will bounce and go right back. Let's draw it. We start low, then go up through the origin, then turn around, then at x equals 1, we come down and just touch it, then shoot back up again. Final example, y equals x cubed. Yeah, I know, bear with me please. Here we can rewrite y as x times x times x. A equals 1 and the y-intercept is 0. And the x-intercepts are 0, 0, and 0. Hang on, that appeared 3 times. When it appears 3 times, it is called a triple root. At a triple root, the curve will flatten near it like a double root does, but it will still pass through. Let's draw it. We start low, then we flatten out to touch x equals 0, then we pass through. There we go, that is why the original y equals x cubed function has that little wiggle in it. It's a triple root. For 2017 students, this expands into polynomial graphs. A polynomial is a function where all powers of x are non-negative integers. For example, y equals 5x to the 4 plus 3x squared plus 2x plus 1. The degree is the highest power of x, in this case 4. The leading term is the term with the highest power of x, in this case 5x to the 4. The leading coefficient is the coefficient of the leading term, in this case 5. The end behavior depends on the sign of the leading coefficient and whether the degree is even or odd. If the leading coefficient is positive and the degree is even, then we start high and end high. If the leading coefficient is positive and the degree is odd, then we start low and end high. If the leading coefficient is negative and the degree is odd, then we start high and end low. If the leading coefficient is negative and the degree is even, then we start low and end low. You can be given polynomials in transformation form where you apply the transformations. The parent functions are quite simple to remember. All the even y equals x to the n look like y equals x squared, except the bottom gets progressively flatter. All the odd y equals x to the n look like y equals x cubed, except the bottom gets progressively flatter as n increases. You can also be given polynomials in factored form, like in this example. Y equals 2 times x plus 1 times x plus 2 times x minus 3 times 4x plus 5. In this case, we multiply the term with x in it in each bracket, and also the number at the start to get the leading term. 2 times x times x times x times 4x equals 8x to the 4. Here, the leading coefficient is a positive 8 and the degree is even, 4. So we start high and end high. Now let's find our x-intercepts, minus 2, minus 3, 3, and minus 5 over 4. No root appears twice, so our line will cleanly cut through all of them. Let's draw it and make sure to turn around after passing each root. Alright, now we just need to find the y-intercept. So substitute x equals 0 and let's see. Alright, all done. Now let's look at reciprocal functions. In Maths Advanced, you only need to know one reciprocal graph, which is y equals 1 over x. For this graph, the key features are the two asymptotes, which quadrants the branches are in, and also the x and y intercepts, if there are any. This graph has two branches. One branch is in the top right, and the other branch is in the bottom left. The most important features are the asymptotes. An asymptote is a line that the graph gets closer and closer to, but never touches. For y equals 1 over x, the vertical asymptote is x equals 0, because x cannot be equal to 0. If x equals 0, we would be dividing by 0, which is not allowed. The horizontal asymptote is y equals 0, because as x gets really big or really negative, 1 over x gets closer and closer to 0. And this parent can be changed into different types when it's in transformation form. For example, y equals a over in brackets b in brackets x minus h plus k. Here, the b in brackets x minus h is what is under the reciprocal, so it is in charge of the horizontal stuff. And a and k are outside. Let's look at an example. Y equals 5 over in brackets 4 in brackets x minus 3 plus 2. Reading off the form, a equals 5, b equals 4, h equals 3, k equals 2. The coefficient of x under the line is already factored as 4 in brackets x minus 3. So inside we do a ht of 1/4 and then a ht right of 3. Outside we do a vd factor 5 and then a vt up of 2. The asymptotes move with the translations. The vertical asymptote starts at x equals 0 and the horizontal translation right 3 sends it to x equals 3. The horizontal asymptote starts at y equals 0 and the vertical translation up 2 sends it to y equals 2. so the asymptotes cross at 3, 2. Because a equals 5 is positive, the branches sit at the top right and the bottom left relative to that new crossing point. That the sign of a, the vertical dilation, controls which quadrants the branches sit in relative to the asymptotes. If a is positive, the branches sit in the top right and bottom left. If a is negative, the graph reflects so the branches sit in the top left and bottom right. In Maths Advanced, you'll often see this form, y equals k over x, where there is only the vertical dilation. You will often be given a point like 1, 2 and be asked to find the value of k, then use the formula to find something, like s equals k over c, read s as sales and c as cost. And you're told that 1,000 sales were made when cost is $20, and then it asks how many sales when cost is $30. Substitute the pair we're given. 1,000 equals k over 20, so k equals 1,000 times 20, which is equal to 20,000. Now the model is complete. S equals 20,000 over c. To find the sales when the cost is $30, substitute c equals 30. S equals 20,000 divided by 30, which is equal to 666.7. And since you can't make part of a sale, that is about 667 sales. Speaking of modeling, let's look at modeling with functions. A model is just a function that describes a real-world situation, just like the S equals 20,000 over C relationship. We had that model's cost and number of sales. But models don't have to be reciprocal functions, they can be anything. Let's look at another common model. For example, suppose a plumber charges a $50 call-out fee and $90 per hour. Let h be the number of hours. Let c of h be the total cost. Then c of h equals 50 plus 90h. That is a linear model. The 50 is the starting amount, and the 90h is the part that changes depending on time. When we use functions in context, we need to think about the domain. Mathematically, h could be any real number, but in real life, the plumber cannot work negative hours. So the contextual domain is h is greater than or equal to 0. This is important. In modeling questions, the HSC often cares about whether your answer makes sense in context. Now let's look at cost and revenue. If c of x is cost and r of x is revenue, then the break-even point happens when c of x equals r of x. Graphically, this is where the cost graph and the revenue graph intersect. It happens when revenue is greater than cost. Rx is greater than c of x. Loss happens when revenue is less than cost. R of x is smaller than c of x. So again, solving the question means comparing graphs. And you can make many more models too. Sometimes Maths Advanced will also give you a half-completed model like y equals 50 times e to the kx. Then you will need to substitute in a pair of values x and y to find k to complete the model before using it. If there are two missing values like y equals a times e to the power of kx, then you would need two pairs of xy values and solve simultaneously to find a and k. But that is just algebra, so we won't go through that in this video. Another modeling terminology is direct and inverse variation. If you're a 2017 student, then you only need to know these two models. If a question says y varies directly with x, then you need to use the half-completed model y equals kx and find k. Direct variation just means that when x increases, y also increases. If a question says y varies inversely with x, then you need to use the half-completed model y equals k over x and find k. Inverse variation just means that when x increases, y decreases. If you are a 2024 student, you will need to know a bit more. The direct variation model looks like this. Still, whenever x increases, y will increase. But instead of y always varying directly with x, y varies directly with x to the power of n. Y equals k times x to the power of n. For example, if y varies directly with x squared, then y equals k times x squared. This will be slightly trickier because sometimes you will need to find both k and n, but you can just substitute two pairs of x and y values and solve simultaneously. For inverse variation, the model looks like y equals k over x to the power of n. For example, if y varies inversely with x squared, then y equals k over x squared. But yeah, whether you're a 2017 syllabus student or a 2024 syllabus student, the key process for modeling is 1. Substitute the given x and y values. 2. Solve for k or n. 3. Write the model. 4. Use the model to answer the question. For inverse and direct variation, the question may not give you the half-completed equation like y equals k over x to the n, so you will need to come up with it yourself. For other models, the question will give you a half-completed equation for you to substitute and find the unknowns, like y equals e to the power of kx. Alright, that's enough about modeling. Let's look at circles and semicircles. A circle is usually not a function, it is a relation. If we use the vertical and horizontal line tests, we can see that it is many to many. The basic circle equation is x squared plus y squared equals r squared. The important parts of a circle when you sketch it are its center, radius, x and y intercepts, if they're easy to find, as well as whether the origin is inside or outside the circle. This comes from Pythagoras. Imagine you have a point x, y on the Cartesian plane. It has a height of y above the x-axis and goes to the right x from the y-axis. If we join the point and the origin, we get a right-angled triangle with its legs equal to x and y. Then this diagonal here is the hypotenuse. Let's call this diagonal length r. Then we can define using Pythagoras that r squared equals x squared plus y squared. And if we set r to a constant, that means we can only choose points that give a triangle whose hypotenuse is that value. But as the hypotenuse is the distance from the origin, that means all the points have the same distance to the origin, hence a radius which is the same all the way around a circle. That is where the equation of a circle comes from. Thus, x squared plus y squared equals r squared. The circle center is 0, 0, and the radius is r. Transformations for circles are a bit different. In Maths Advanced, we only need to know how to change the center, and we do not use transformation form for it because we cannot put y by itself since it is not a function. We would get a plus or minus square root of r squared minus x squared, so we would end up with two functions, but more on that when we get to semicircles. In Maths Advanced, we just need to know how to do a horizontal and vertical translations by replacing x with x minus h and y with y minus k. So that means the whole thing shifts right h units and up k units. X minus h squared plus y minus k squared equals r squared. So the center goes from 0, 0 to hk, and the radius is still r. If you want to make the circle larger or smaller, you don't use vertical and horizontal dilations, because you can just change the radius instead. It is much easier. Let's do an example. We'll sketch the equation of a circle. Let's look at the equation. X squared plus y squared plus 4x plus 6y plus 12 equals 5. Oh no, the circle is a mess. We can barely tell that it is a circle. It kind of looks like a quadratic. But remember, if you have x squared and y squared both in it with the same coefficient, it is a circle. When a circle is a mess like this one, use complete the square to clean it up. Let's move all the constants to one side and group the terms with x and the terms with y together. X squared plus 4x plus y squared plus 6y equals 5 minus 12. That looks nicer. Now let's complete the square. We'll add 4 and 9 to both sides. X squared plus 4x plus 4 plus y squared plus 6y plus 9 equals 5 minus 12 plus 4 plus 9. Now let's factorize. X plus 2 squared plus y plus 3 squared equals 6. Now that looks like something we can sketch. We can read off that the center is minus 2 minus 3 and that the radius is the square root of 6, not 6. Let's plot the center. Lovely. Now let's add root 6 and subtract root 6 to find the top and bottom and left and right. Let's see where the top point of the circle goes first. That point would be minus 2 minus 3 plus root 6. Now I'm not sure if that goes above or below the x-axis, so let's calculate minus 3 plus root 6 in my calculator. Okay, that is a negative value, about minus 0.55, so it goes below the x-axis. Alright, now we have 5 points on there and we're ready to draw a circle. But I'm not sure if the origin goes inside the circle or not, because my drawing might not be entirely to scale, which is fine. but if I get it wrong, I can lose marks. So I will substitute the point 0, 0 into my equation and see what I get. 0 plus 2 squared plus 0 plus 3 squared equals 4 plus 9, which is equal to 13. 13 is greater than 6. If it is bigger than the value of r squared, then that means it's outside the circle, because r squared is just about the distance from the center of the circle. So if it's bigger, then that means it's far from the center, which means it's outside. If it's smaller than r squared, then it means it's inside the circle. If it's equal to r squared, then that means the origin is on the circle. Quick aside, if you ever substitute the origin and the left side comes out to exactly r squared, the origin sits right on the circle, so the curve passes straight through 0, 0. Okay, in our case 13 is greater than 6, so that means our origin is outside the circle. Lovely, done. Now let's find the y and x intercepts. We won't usually bother, but this question told us explicitly to do that, so we'll do it. Sub x equals 0 and y equals 0. Alright, lovely, everything looks great. Note that often in advanced you won't need to do all of this. It is usually a combination of the steps we just did. Like sometimes you'll need to find the x and y intercepts but not need to shift to the center, etc. You don't always have to plot all 4 points above, below, left and right of the center, but if you're not familiar, you can always start with that if unsure. So in a nutshell, to graph a circle, 1. Plot the center, 2. Move r units left, right, up and down, 3. Check if the origin is inside, outside or on the circle, 4. Sketch the circle through those 4 points and the origin if needed, and 5. X and y intercepts if the question asks. Now, as promised, let's discuss semicircles. Semicircles are what happens when you solve the circle equation for y or x. From x squared plus y squared equals r squared, if we solve for y, we get y equals plus or minus square root r squared minus x squared. Well, that's two functions, so we'll have to pick one. If we pick y equals plus square root r squared minus x squared, that is the top semicircle, since y is always positive. And if we pick y equals minus square root r squared minus x squared, that is the bottom semicircle, since y is always negative. Similarly, if we solve for x, we get x equals plus or minus square root r squared minus y squared. That is two functions, so we need to pick one. If we pick x equals plus square root r squared minus y squared, that is the right semicircle, since x is always positive. And if we pick x equals minus square root r squared minus y squared, that is the left semicircle, since x is always negative. You can do horizontal and vertical shifts for semicircles too by replacing x with x minus h and y with y minus k. Again, you don't need to do dilations because you use the radius instead. Now let's look at exponential functions. The parent exponential function is y equals a to the x, where a cannot equal 1 since 1 to the power of anything is 1 and we'll just have a flat line at y equals 1, and also a must be positive. Its key features are that it always has a y-intercept of 1, as any number to the power of 0 is 1, and it is also always positive and has a horizontal asymptote at y equals 0. If a is greater than 1, then the curve will be increasing, since it is a large number multiplying by itself over and over. If a is between 0 and 1, then the curve will be decreasing, since it is a small number multiplying by itself over and over. Let's try graphing 1. Y equals minus 3 times e to the power of minus 5x plus 1 plus 2. Remember, e is just a number, Euler's number. This looks like a mess. In Maths Advanced, the mess is always because of transformations, so let's take care of it with transformation form. Minus 5x plus 1 is inside the function e to the x, so that is in charge of the horizontal stuff. We need the coefficient of x to be 1, so let's factor out minus 5. Doesn't matter if we get a fraction. Minus 5 in brackets x minus 1 over 5. Nice. Now we know we get a horizontal dilation of factor minus 1 over 5, and then shift to the right by 1 over 5. A negative dilation just means we reflect first, then dilate by 1 over 5. Let's look at the vertical transformations. We will look at the negative 3 and plus 2. That means we dilate vertically by a factor of minus 3 and then translate up by 2. Let's do all those transformations. We'll start with the function e to the x. Let's graph it. Let's draw the y-intercept and the asymptote first. Lovely. Now I'll put e in my calculator. It is 2.71, which is bigger than 1, so it's increasing. Let's draw the curve. Lovely. Now let's list out our transformations. I will do both dilations first, then both translations. This is totally fine, by the way. As long as each dilation is done before its corresponding translation, we're good. Okay, let's dilate horizontally by factor -1/5. That means I flip in the y-axis, then dilate by 1/5. Let's flip this. Now it's decreasing. And now it looks a bit narrower and decreases faster. Cool. It doesn't have to be to scale, don't worry. Let's dilate vertically by factor -3. Let's flip vertically first. The y-intercept turned to -1, and then dilate by factor 3. Cool, the y-intercept turned into -3. Looks nice. Now let's do translations. Let's do the vertical one first because it looks easier. To move up by 2, let's move the horizontal asymptote to y equals 2, then move the curve up with it. The y-intercept is now -1. Lovely. Okay, now the horizontal translation. Let's move to the right by 1/5. The horizontal asymptote stays the same and our point 0 - 1 turns into 1/5 - 1. Looks nice. Alright, we've done all the transformations, but it is always good to have at least 2 points on the curve, so let's find another one. Let's find the y-intercept, since we lost it after the horizontal translation. Substitute x equals 0. Y equals -3 times e to the power of -5, 0 plus 1, plus 2, which is equal to -3 times e plus 2, which is equal to -3 times 2.718 plus 2, which is approximately -6.15. So the y-intercept is about 0 - 6.15. Alright, let's label it. Lovely. Done. So in a nutshell, when graphing exponentials in transformation form, track 1. Look at the parent function y equals a to the x and plot the y-intercept 0, 1 and the horizontal asymptote y equals 0. 2. Decide if a is bigger than 1 and draw the growth or decay curve. 3. Apply all transformations. 4. Make sure you have at least 2 points. Now let's look at logarithmic functions. But first, what is a logarithm? Let's look at this simple fact. 2 to the power of 3 is equal to 8. There are many ways to ask questions using the language of math about this fact. For example, what is 2 to the power of 3 becomes 2 to the power of 3 equals, and what base to the power of 3 gives 8 becomes the cube root of 8. But what if we want to ask, what power does 2 need to be raised to get 8? We don't have an expression for it. But that's what logs are for. We call it log base 2 of 8, which is equal to 3, since 2 needs to be raised to the third power to be 8. That is what a logarithm is. In Maths Advanced, we need to know how to graph these functions too. Let's graph y equals log base 2 of x, where y is the value that 2 needs to be raised to the power of to equal x. The base curve will look like this. The point 1, 0 is always on the curve, and there is always a vertical asymptote at x equals 0. Hang on, that feels familiar. It feels like the exponential functions, but a bit different. That's because it is. Logs are the inverse functions of exponentials, which means they will undo an exponential. So if you have a term x, and then do an exponential function to get e of x, and then do a log function on that, log base e of e of x, then you will get x back. That is very helpful when you are working with algebra to find x. For example, e to the power of x equals 5. Log e to the x equals log e 5. X equals log base e of 5. And you can use them for inequalities too, but be careful when to flip the sign. But that is algebra and we will cover it in another video. The importance of inverse functions is that they are reflections of each other in the line y equals x. So if we draw y equals e to the x and y equals ln x on the same axes, then rotate the axes so it's easier to see, they are symmetrical about the y equals x line. By the way, ln is just a quick way to say log base e, and log is just a quick way to say log base 10. Each point on ln x is just the point on e of x, but with the x and y values swapped. For example, 0, 1 on e of x becomes 1, 0 on ln x, and the horizontal asymptote y equals 0 becomes the vertical asymptote x equals 0. Alright, now let's learn how to sketch any logarithm that can possibly appear in the Maths Advanced syllabus ourselves. The checklist is very similar to exponentials. To sketch the parent function log base a of x, 1. Plot the point 1, 0 on the axes. 2. Plot the x equals 0 vertical asymptote on the axes. 3. Decide if a is greater than 1. If so, it is increasing. If not, it is decreasing. Note that like in exponentials, a cannot be negative or equal to 1. Then apply transformations. 4. Ensure there are 2 points on there. 6. If the question asks, or if they are easy to find, plot the x and y intercepts. Note that if you see a weird logarithm like ln of x squared and cannot graph it with transformations, you will need to apply log laws. In this case, we can rearrange to 2 ln x, which shows it is just a vertical dilation by factor 2, which is quite easy to sketch. We won't cover log laws in this video since it is about algebra, but just a note. Alright, we've done quite a lot of different functions. Now let's piece things together with piecewise defined functions. A piecewise function is a function with different rules on different parts of the domain. For example, fx equals x when x is greater than or equal to 0, and it is equal to minus x when x is smaller than 0. To graph a piecewise function, we simply graph it piece by piece. Let's graph that one. Let's look at the first piece, fx equals x where x is greater than or equal to 0. Alright, that means we'll only be drawing in this region here. If the restriction confuses you, you can always draw on the full domain, then rub out the other bits. Okay, let's draw it. It goes through the origin, and let's also plot the point 1, 1. Lovely. Now let's look at the second piece. F of x equals negative x when x is smaller than 0. That means we'll be drawing in this domain. Let's draw it. Our line goes almost up to the origin, but not at the origin, since x equals 0 is outside this domain. Note that when defining a piecewise function, there is no x values that appears in 2 different pieces, by the way. Okay, let's draw it. Let's label the point negative 1, 1, so it is clear exactly where the line is. Wonderful. That is our piecewise function done. Does it look familiar? This example is actually the absolute value function, y equals the absolute value of x. Absolute value means distance from 0, so absolute value of 5 equals 5, and absolute value of negative 5 is also equal to 5. That is why the graph is always above or on the x-axis. The graph we just drew is the parent graph y equals absolute value of x, so make sure you remember what it looks like so you don't need to figure it out every time. If you use the transformation form, you can graph any function that looks like y equals a absolute value b in brackets x minus h plus k by transforming the original function. The absolute value function's interesting bits are its branches as well as its sharp point, the corner, which is at the origin for y equals absolute value of x, so be sure to label that point when sketching. It is also symmetric about the y-axis. The x and y intercepts are easy to find for this curve, so it is good to use them for your second and third points. When drawing piecewise functions, you want to have at least one point on each piece to show that it is that piece. So in a nutshell, to draw piecewise functions, 1. Graph the first rule only on its domain. 2. Graph the second rule only on its domain. 3. Use open or closed circles at endpoints if needed. For 2024 students, you also need to know square root of x squared is equal to the absolute value of x. This is because squaring makes the value positive and then square rooting gives the non-negative magnitude. Even if you're a 2017 student, this is good to know because it is helpful when solving equations, like so. Absolute value 2x plus 3 equals 5. We can change that to the square root of 2x plus 3 squared equal to 5. So 2x plus 3 squared is equal to 25, and 2x plus 3 is equal to plus or minus 5. Then solve 2x plus 3 equals 5 and 2x plus 3 equals negative 5 separately. You can jump to this step straight away when you're used to it. Alright, that's all the graphs you need to know for Maths Advanced. Now let's look at what the meaning of all this is. We've learned the algebra and the geometry, now we need to connect them. Imagine we have a function f of x. If you solve f of x equals 0, you are finding the x-intercept. If you solve f of x equals k, you are finding where the graph intersects the horizontal line y equals k. If you solve f of x equals g of x, you are finding where the two graphs intersect. And if you solve f of x is greater than g of x, you are finding where the graph of f is above the graph of g. So equations and inequalities are not separate from graphs. In fact, often you will need to use algebra to find where two graphs intersect for calculus. or solve inequalities involving complex functions that we can't do algebraically. Alright, now we've learned about all the theory, graphs, and how to connect the theory to the graphs. We need one final extension that allows us to find the more complex questions. Often, functions can be put together to create a new function. So if you had two functions, f of x and g of x, you could add, also called the sum, f of x plus g of x. Subtract, also called the difference, f of x minus g of x. Multiply, also called the product, f of x times g of x. Divide, also called the quotient, f of x divided by g of x. And put them inside each other, also called composite, f of g of x or f o g of x. And you can do that with 3 or more functions too. Let's go through each of them and find their domain, range, odd or even, as well as how to graph them, with examples f of x equals 2x and g of x equals x squared. First of all, adding two functions. F of x plus g of x equals x squared plus 2x. The domain is the intersection of f of x and g of x. That is, for x to work in the sum, x must be allowed in both of the summed functions. The range is harder to see, so compute the sum f of x plus g of x first, then graph to see it. To find odd, even, or neither, compute the sum and test normally by replacing x with minus x. To graph, compute the sum and graph normally. Now, subtracting two functions. F of x minus g of x equals 2x minus x squared. The domain is the intersection of f of x and g of x. That is, for x to work in the difference, x must be allowed in both functions. The range is harder to see, so compute the difference f of x minus g of x first, then graph to see it. To find odd, even, or neither, then compute the difference and test normally by replacing x with minus x. To graph, compute the difference and graph normally. Now, multiplying two functions. F of x times g of x is equal to 2x times x squared, which is equal to 2x cubed. The domain is the intersection of f of x and g of x. That is, for x to work in the product, x must be allowed in both functions. The range is harder to see, so compute the product f of x times g of x first, then graph to see it. To find odd, even, or neither, then compute the product and test normally by replacing x with minus x. To graph, compute the product and graph normally. Now, dividing two functions. F of x over g of x is equal to 2x over x squared. Here the domain is the intersection of fx and g of x minus the values of x that make g of x equal to 0, since you can't divide by 0. This can be seen quite clearly in the above option. You can see it in the quotient function 10x, which is sin x over cos x. Whenever cos x is equal to 0, there is an asymptote in tan. So you can clearly see that. Even if both sin and cos allow all real x, tan x does not. The range is harder to see, so compute the quotient f of x over g of x first, then graph to see it. To find odd, even, or neither, then compute the quotient and test normally by replacing x with minus x. To graph, compute the quotient and graph normally. Finally, a composite function means putting one function inside another. If we have f of x equals x squared and g of x equals x plus 1, then f of g of x means first do g, then put the result into f. So f of g of x is equal to f of x plus 1. Since f squares its input, f of x plus 1 equals x plus 1 all squared. The order matters. G of f of x would be different. First do f. F of x equals x squared. Then put that into g. G of f of x equals x squared plus 1. So usually f of g of x is not equal to g of f of x. Now the domain matters. For a composite function like f of g of x, the domain is harder to see. It is the x values that go into the inner function g of x, and whose output g of x is then allowed as an input of the outer function f. So the input must be valid for g first, and then g's output must also be valid for f. This is very difficult to see, so it is always good to compute the composite function first before finding the domain, range, graphing it, or determining odd and even. For those who really want to think, a composite function is always even if the inner function is even. I'll leave you to ponder on that. For 2017 students, if you want to determine if a combined function is 1-to-1 or many-to-1, use the horizontal line test. Alright, that's it. The whole functions topic can be compressed into 5 ideas. 1. A function is a rule. 2. A graph is a picture of the rule. 3. Transformations move the picture. 4. Solving graphically means finding intersections. 5. Domain and range tell you what values are allowed. So, now you know everything you need for the HSC. Alright, as promised, yes, I took notes for you and I'm going to show you where they are. If you log on to my website called studeroo.com.au, make an account, then select Maths Advanced as a subject, you will be at the dashboard page. From there, you can head to the Notes tab. Under Studeroo's Notes, you will see Functions Crash Course, where you can review notes anytime you want. Alright, you are probably feeling confident right now that you know how it all works. But there's always that daunting moment where you're like, this makes so much sense, and then you look at HSC and trials questions and suddenly all the confidence goes away. Well, good news, we can work on that together too. If you head to the Syllabus tab, you can see every single skill for Maths Advanced, just like we've covered, with videos explaining new concepts if you feel like something is still fuzzy in the exam. For example, if you're confused about the domain of a function, you can click on this video about the domain and watch how it's done. You can also see how often domain is quizzed directly in the HSC. In this case, not too much. Best of all, after you've watched the video and are confident, you can go straight to the HSC questions at the bottom that are exactly about what to practice. What if I get a question and everything goes out of my head, you ask? No problem. Studeroo has a syllabus solution right beneath the question that you can look at. Additionally, if you do not want to look at the answer straight away but want guidance through it, you can use the DIY approach and get hints that walk you through step by step. Finally, you can also watch the question itself get explained with a brilliantly set out interactive video. In the video, if something doesn't make sense, you can simply click to ask and Studeroo AI can explain that exact part. No copy pasting to AIs like Claude or GPT. Even better, Studeroo AI is trained in teaching students in ways that make sense. It is also syllabus grounded, so you'll never see it use PhD level math to explain your questions. If something in a question is still not clicking, you can click the syllabus tag at the top. It will take you straight to the exact syllabus dot point, along with the content video that teaches it, so you can quickly go back, learn what you need, and return to the question. If you look at the notes section within a question or a syllabus dot point, you can make your own self-notes that you learned in the question for future reference, so you never lose anything you learned. You can review them all in one place later on. No more random notes lost in physical past papers. The Studeroo website is there for you anywhere you go. Most importantly, Studeroo is constantly improving. Today, there are over 2,000 videos on it and more are added each day. Make sure to check out your notifications to see when new exam tips, papers, and features come out. Studeroo is designed to help you study the exact way I did, by constantly cycling between practice questions and reviewing only the content you actually need. But lucky for you, you don't have to dig through the internet searching for resources. Everything is already there, right when you need it. So what are you waiting for? Go to studeroo.com.au and start flying.